Hi, I'm Molly, and this is the Wireless Systems Project. This presentation will discuss the completion of Task 1 of Project Week 2, which is the Wireless System Project, and this is a quick overview of what we'll be talking about today. So the objectives of this presentation are to increase understanding of how radio propagation environments vary, to discuss the process of attaining the findings, and consider why these findings occurred. For this project, we used an Arduino Nano and a custom wireless communications module that acted as a receiver. This was paired with a transmitter that was located in 2 East 2.14. This was a low-power transmitter, so it operated at a safe level of non-ionizing radiation, so it wasn't going to cause harm to anyone. And the frequency of 868 megahertz meant that no license was needed to use this bandwidth. So the initial aim of this task was to map 2 East Level 2 by recording the signal propagation at every meter around the department corridors. By doing this, we found that the signal strength decreased as the distance between the transmitter and the receiver increased. But it should be noted that in some areas the signal quality was poor despite the distance being fairly short, which assumes that another variable was impacting the results. So let's have a look at what the ideal values would have been. This is the Friss equation, where the power received equals the transmitter power multiplied by the gain of the transmitting antenna, multiplied by the gain of the receiving antenna, multiplied by lambda over 4 pi d squared. This equation allows us to calculate the ideal power, assuming that there were no losses. However, for this practical, we didn't know what the antenna gains were, so it wasn't particularly useful to us. So we rearranged it to get it in this form, where the distance is compared to the received power at a calibrated distance. We used a distance of 1 meter away, which was 31.6 nanowatts, so obviously a very small power. This equation allowed us to calculate the ideal for any equation, but calibrating each one of these by hand would have taken a lot of time and would have been very prone to errors and wasn't very scalable, so we needed to find a more scalable approach. We decided to implement this into Python. Initially, we broke down the steps into a flowchart to see what we needed to do and see what methods and classes we needed creating, which meant that it was quite easy once we got into Python to put this together. We used 3 main methods, so you had to define self. We also used getAntennaDistance, which calculated the Pythagorean distance, as from the floor plan it was much easier to work out the horizontal and the vertical distance than it was to work out the exact distance to it, so it could do that for you. And also it could calculate the Friss equation for you. We also used a static method, which added the calculated readings to a dictionary, which then went into a list. So when you finished running the code, it could print all of these in the terminal for you in a way that was really easy to see and store. This approach meant that each new reading only required 1 new line of code to tell the program the inputs, rather than having to do a whole new set of calculations by yourself and keep track of what's what. So this is just one of the example of outputs that we found. There are multiple things to note about these findings. None of the readings are as strong as the ideal value, meaning that there were always some losses present, just some bigger than others. We found that an increase in distance decreased the signal power, which is what we expected. We found that noise created interference within the signal. For example, when people walked past when you're trying to take the readings, or even when you just stood still, there was a lot of variation within them, so you had to write down more of a mean average. And we can also conclude that barriers such as doors and walls dampen the signal, which contributed to the losses. I'm sure if these readings were taken inside the lab in the room it was, they would have been a lot higher, but every reading we took was behind 1, 2, 3 doors within the corridor. So that's it. Thank you for listening about the Wireless Systems Project.